Good morning, ladies and gentlemen. I'm Ye Wang from Xiamen University. First of all, I would like to thank the organizing committee and the meeting chair, Professor Enrique Iglesias, for the kind invitation. It's my great pleasure to give a plenary lecture in video for the record of the 17th International Congress on Catalysis, which unfortunately couldn't be held due to the COVID-19 pandemic. I will talk about selectivity control in catalytic transformation of C1 molecules into multicarbon products. I will first say a few words about background, then I will present our work on selectivity control in CO2 hydrogenation to multicarbon products, that is C2 plus products, electrocatalytic reduction of CO2 to ethylene and ethanol, photocatalytic coupling of methanol to ethylene glycol, and finally, conclusions. First, background. C1 molecules, including methane, methanol, formaldehyde, formic acid, CO, and CO2 are abundant carbon feedstock that can be derived from various non-petroleum carbon resources, such as natural gas or shale gas, coal, biomass, or even carbon dioxide. On the other hand, the multicarbon compound, that is C2 plus compound, including hydrocarbons such as the lower olefins, aromatics, liquid fuels, and oxygenates such as ethanol and ethylene glycol, are key chemicals in the chemical or energy industry. The direct conversion of C1 molecules to high-value C2 plus compounds involving CC coupling is of high significance. The Fischer-Tropsch synthesis is a classic C1 chemistry process for the hydrogenation of a C1 molecule to C2 plus compounds, including both olefins and paraffins. And iron carbide, cobalt, metallic cobalt, and metallic ruthenium are efficient catalysts for Fischer-Tropsch synthesis. The selectivity control is the key challenge for FT synthesis. It is generally accepted that FT synthesis proceeds through the dissociation of CO, the generation of CHX species, the coupling of CHX species to C and HM intermediates with different carbon numbers, and the formation of products via hydrogenation or dehydrogenation. The key to the product selectivity is the CC coupling and the chain growth process. Unfortunately, the chain growth on FT metal or metal carbide surfaces is uncontrollable. So the product selectivity generally follows the Anderson-Schwarz flow distribution. The selectivity toward a specific range of C2 plus hydrocarbons is limited. For example, the maximum selectivity to C2 to C4, including both olefins and paraffins, is 58%. For CO2 hydrogenation, iron-based catalysts have shown unique performance for the formation of C2 plus hydrocarbons. Typically, the reverse water-gas shift reaction first occurs on iron oxide, and then the form syngas undergoes Fischer-Tropsch synthesis to olefins or paraffins on iron carbide. Therefore, the product selectivity in CO2 hydrogenation also follows the Anderson-Schwarz flow distribution. For the conversion of methane, another important C1 molecule, methane can undergo oxidative coupling or non-oxidative coupling both at high temperatures. Methyl radical is the key intermediate for both oxidative coupling and non-oxidative coupling. But the high temperature leads to limited selectivity of C2 products due to the formation of CO2 or coke. Methanol undergoes dehydrative coupling to lower olefins or aromatics through MTO or MTA process. So the shape selectivity of zeolite controls the product selectivity, but the precise control selectivity toward a specific product is still difficult. So in such background, we focus on the challenging research topic, that is the selectivity control in transformation of C1 molecules involving CC coupling. We aim to develop new strategies and routes for selectivity control in hydrogenation of CO, CO2 to C2 plus compounds to break the selectivity limitation, to design efficient electrocatalytic and photocatalytic systems for the activation of inert CO2 and CH bond under mild conditions, offering new possibility to control the selectivity of C2 plus compounds, and to accumulate knowledge of the mechanism related to CC coupling from C1 molecules to enrich C1 chemistry. So next, I will present our studies on the selectivity control in CO, CO2 hydrogenation to C2 plus products. So we have developed several strategies for selectivity control in CO hydrogenation. So the first strategy is to combine FT active component for the hydrogenation of CO to heavy hydrocarbons with another active component that can perform selective CC cleavage to fabricate one bifunctional FT catalyst to tune the selectivity of liquid fuels. So the second strategy is to integrate methanol or dimethyl ether DME synthesis catalyst with a zeolite catalyst for the selective CC coupling to construct bifunctional catalyst for the direct conversion of syngas to lower olefins and aromatics. So the third strategy is to combine methanol DME synthesis and methanol or DME carbonation to C2 plus oxygenates with precise controlled CC coupling step. So I'll give examples for these three strategies. For syngas to liquid fuels, we combine FT metal nanoparticles for CO activation and CC chain growth, and mesoporous zeolite for selective CC cleavage into one bifunctional catalyst. By regulating the acidity and mesoporous zeolite, we succeeded in tuning the selectivity to specific liquid fuels. We obtained diesel, jet fuel, and gasoline with selectivities of 65%, 72%, and 74% respectively by simply changing the cation in mesoporous zeolite. We have developed new bifunctional catalysis beyond FT synthesis for the direct conversion of syngas to lower olefins. We integrate syngas to C1 intermediate, that is methanol and dimethyl ether DME, and C1 to lower olefins in tandem with one bifunctional catalyst. Metal oxide such as zinc, zirconium oxide, zinc aluminate, and zinc gallate with spinel structure is efficient for high temperature methanol synthesis, which matches well with the MTO catalyst. Metal oxide is also very unique towards CO hydrogenation to methanol or DME while keeping the product lower olefins from further hydrogenation to paraffins. The product selectivity is mainly controlled by the pore structure of zeolite, that is, its shape selectivity. The selectivity of lower olefins reached 80% at CO conversion, 40% by using sulfur-34. So this selectivity is significantly higher than the maximum value, that is 58% predicted by the ASF distribution. We found that the acidity of zeolite in the bifunctional catalyst affected the reactions inside zeolite cages. Take SSZ13, which has the same topology with sulfur-34, and an example of zeolite component. CO conversion was low on the catalyst without bronzed acid sites, and methanol and DME were the major products. This is because methanol synthesis is thermodynamically limited under such conditions. CO conversion increased significantly with the density of bronzed acid sites. This is not because the bronzed acid site can catalyze CO activation and conversion, but we think that the occurrence of subsequent MTO reaction on bronze acid sites could thermodynamically drive the syngas conversion of metal oxide, therefore increasing the CO conversion. Upon increasing the density of bronze acid sites, methanol and DME are transformed into lower olefins, but a too higher density of bronze acid sites leads to the conversion of lower olefins to paraffins. Therefore, bronze acid sites are active sites for CC coupling, but their densities should be controlled. These results confirm that methanol and DME are reaction intermediates in our system. We have further investigated the effect of the proximity of two active components. We clarified that the separation of the two components in two catalyst beds in one reactor only provided a very low CO conversion and lower olefin selectivity. The increase in the proximity increased the conversion of CO and the selectivity of lower olefins. We speculate that the quick transfer of methanol and DME from metal oxide to supersulfur or SSZ13 zeolite favors the formation of lower olefins. By changing the zeolite, different types of products can be expected. For example, the use of ZSM5 instead of supersulfur to fabricate the bifunctional catalysts results in the formation of aromatics with selectivity of 80% at CO conversion of 20%. We further found that the bifunctional catalyst showed superior stability. It is well known that zeolite supersulfur or ZSM5 used in the conventional MTO or MTA process undergoes quick deactivation due to the coke deposition. Our bifunctional catalyst for the conversion of syngas to lower olefins or aromatics is significantly more stable. For example, this zinc zirconium oxide ZSM5 bifunctional catalyst is stable for 1,000 hours during the conversion of syngas to aromatics. Our studies suggest that the presence of hydrogen in syngas, the lower methanol DME concentration in zeolite, and the lower density of bronze acid sites in zeolite adopted in this work should be the major reasons for the higher stability. So our studies demonstrated that the bifunctional catalysis with methanol and DME intermediate is also an effective strategy for the hydrogenation of CO2 to lower olefins or aromatics. Zinc zirconium oxide, zinc gallate, and zinc aluminate are excellent metal oxide candidates, while zeolite controls the product selectivity. So over this zinc aluminate supersulfur catalyst, the selectivity of lower olefins reached 87% at CO2 conversion of 15%. So over this zinc zirconium oxide ZSM5 bifunctional catalyst, the selectivity of aromatics reached 76% at CO2 conversion of 16%. So these selectivity values are much better than those obtained over iron-based catalysts. Unlike transition metal catalysts, on which the activation of CO, CO2, and hydrogen has been studied intensively, the activation of CO, CO2, and hydrogen on metal oxides is less understood. So using zinc aluminate as an example, we have investigated the mechanism for the activation of these small molecules on the basis of the characterizations by ESR, CO, CO2 chemisubstitution, FTIR, and hydrogen deuterium exchange reaction. We propose that CO and CO2 is activated on oxygen vacancies, while hydrogen is heterolytically activated on zinc oxygen domain, forming hydride and proton for hydrogenation and protonation. Format and methoxy species are major adsorbed species on oxide surfaces in both CO and CO2 conversions. We believe that unlike hydrogen atom formed on metal surfaces, the while hydrogen is heterolytic species on oxide surfaces possess unique hydrogenation ability, keeping the lower olefins from further hydrogenation. The conversion of syngas to C2+ oxygenates, such as ethanol, has attracted much recent attention. Many catalysts have been reported for the direct conversion of syngas to C2+ oxygenates, in particular ethanol, but the selectivity is generally lower than 60%, even at a lower CO conversion. It is generally accepted that the coupling of CHX and CO, or CNHM and CO, is responsible for the formation of ethanol or higher alcohols. Thus, both dissociative and non-dissociative CO species are needed. The non-dissociative CO may form methanol, while the dissociative species may be converted to methane and C2+ hydrocarbons. In other words, there are multiple reaction channels on catalyst surfaces, making the control of selectivity to target a product very challenging. Our strategy is to design tandem catalysts for one-channel CO to ethanol. So our idea is that tandem catalysis via methanol or DME and acetic acid or methyl acetate by integrating metal oxide for methanol DME synthesis and MOR zeolite for methanol and DME carbonation and metal nanoparticles for the hydrogenation of acetic acid or methyl acetate may accomplish the one-channel high selective conversion of syngas to ethanol. So it should be noted that the methanol DME carbonation catalyzed by mordanite zeolite is a key step for the precise CC coupling here. As you can see, the single zinc aluminate provided DME as a major product in syngas conversion. We discovered that the combination of mordanite with zinc aluminate in two catalyst beds in one reactor offered methyl acetate and acetic acid as major products. The selectivity of methyl acetate and acetic acid was higher than 85%. By adding a third catalyst layer of zinc aluminate in the downstream of mordanite, we obtained ethanol as a major product with a selectivity of 52%. These results clearly suggest the relay catalysis, that is, syngas to DME on metal oxide, the carbonation of DME to methyl acetate on mordanite zeolite, and the hydrogenation of methyl acetate on zinc aluminate, leading to the formation of ethanol. So methanol was also formed with some hydrocarbons. If we further add MOR layer, a mordanite layer in the downstream of zinc aluminate, ethylene was formed as a major product with a selectivity of about 50%. Thus, the dehydration of ethanol on this mordanite layer results in the ethylene. The mixing of zinc aluminate and MOR zeolite and further increasing their proximity, increasing the ethylene selectivity to 65%. And the selectivity of C2 to C4 olefins is about 80%. So in short, by changing the arrangement of the two components, zinc aluminate and mordanite zeolite, we succeeded in producing methyl acetate, ethanol, and ethylene as the major products. So the relay catalysis strategy enables the synthesis of different C2 compounds, including methyl acetate, ethanol, and ethylene from syngas. However, this route via DME and methyl acetate can only provide a maximum single-pass ethanol selectivity of 67% because of the formation of methanol during the hydrogenation of methyl acetate. So to improve the single-pass ethanol selectivity, the reaction intermediate should be precisely controlled. That is to say, to control the selective formation of methanol and acetic acid intermediates by careful catalyst design in each step is the key to obtaining high ethanol selectivity. We found that a potassium-modified zinc zirconium catalyst showed high selectivity of methanol, 93% selectivity of methanol. The combination of this metal oxide with zeolite morganite with the illumination of aluminum in 12-membered ring channel offered acetic acid with selectivity of 84%. A further addition of a hydrogenation catalyst, that is platinum tin loaded on silicon carbide, offered ethanol with a selectivity of 70%. By optimizing the three-component relay catalysis system and operation conditions, the selectivity of ethanol could reach 80% at the CO conversion of 22%. Although the three components work independently in the relay process, there exist synergistic effects in the system. In the traditional methanol carbonation, zeolite morganite undergo quick deactivation due to coke deposition, whereas the presence of hydrogen in syngas significantly enhances the stability of morganite zeolite for methanol carbonation. We also found that the presence of CO in the hydrogenation reaction poisoned the supported platinum catalyst, and the addition of tin in the catalyst could avoid the catalyst poisoning by weakening the CO chemisoption. So next, I would like to move to the topic of electrocatalytic reduction of CO2 to ethylene and ethanol. Besides thermocatalytic hydrogenation of CO2 to various products, electrocatalytic and photocatalytic reduction of CO2 with water have recently attracted much research attention. So electrocatalysis and photocatalysis can proceed under mild conditions, not only having the advantages in harnessing the renewable energy to store chemical energy, but also offering the potential to synthesize target products with high selectivity. As compared to photocatalysis, so electrocatalysis has demonstrated a better performance for the conversion of CO2 to C2 plus compounds, in particular ethylene and ethanol. Conventionally, the H cell is adopted for electrocatalytic CO2 reduction, but the current density is usually lower than 100 milliampere per square centimeter due to the limited CO2 solubility in aqueous solution. The use of flow cell with gas diffusion electrode enables a direct feeding of CO2 to electrode and electrolyte interface to circumvent the mass transport limitation, resulting in industrially relevant high current density. It is generally believed that the strength of CO absorption on a metal catalyst determines the product in the electrocatalytic CO2 reduction reaction. Among different metal catalysts, copper shows unique property in the formation of C2 plus compounds owing to its medium CO absorption strength. Ethylene and ethanol are the major C2 plus products on copper catalysts, but other products, including hydrogen, formic acid, CO, and methane, are still formed, leading to lower Faradic efficiency of C2 products on pure copper catalysts. So many studies have been devoted to involving the Faradic efficiency of C2 plus products, many by tuning the absorption of CO on catalyst surfaces by, for example, increasing the ratio of C plus to C1 plus to C0 with some anion modifiers by alloying copper with gold, silver, aluminum, and zinc, by tuning basicity and hydrophobicity by modification with organic molecules. Although significant progress has been achieved, it's still challenging to achieve both high C2 plus Faraday efficiency and high activity. We have been working on the design of copper catalysts with both CO adsorption and hydrogen activation centers with an aim to achieve both high activity and selectivity. So we construct C1 plus site to enhance CO adsorption and a fluoride site to accelerate water activation by strong covalent interactions with potassium hydrate. So water activation might enhance the undesirable hydrogen formation, but our recent studies demonstrated that suitable water activation plays a role in obtaining high activity in CO2 reduction. So based on these ideas, we fabricated fluoride modified copper catalysts by Solve-Sumer method followed by electroreduction. The presence of surface fluoride species and copper plus sites have been confirmed by XPS and in situ Zen's characterizations. So our electrocatalytic CO2 reduction experimental results show that the introduction of fluoride into the electrolyte only slightly changes the catalytic performance because fluoride is difficult to be absorbed on copper surfaces. On the other hand, the modification of fluoride on copper surfaces significantly enhanced C2 plus Faraday efficiency and the current density. So the C2 plus Faraday efficiency increased from about 40% to 81%. Further, we found that the modification of copper by halide could also increase C2 plus Faraday efficiency and the current density. The C2 plus Faraday efficiency and the current density increased with the electronegativity of the halogen. And fluoride modified copper catalyst offers highest C2 plus Faraday efficiency and also the current density. Further optimization of the performances of the fluoride copper catalyst by changing the applied potential and changing the CO2 flow rate demonstrate that the current density could reach 1.6 ampere per square centimeter, and C2 plus Faraday efficiency was kept at 80%, outperforming most electrocatalysts reported so far to date. The single-pass CO2 conversion reached about 19%, and C2 plus selectivity was about 86%, offering single-pass C2 plus yield of 16.5%. Such a combination is even better than those for thermocatalytic hydrogenation of CO2 and high temperatures and high pressures. So to develop long-term stable electrocatalyst for CO2 reduction reaction is a challenging research goal. Our fluoride modified copper catalyst is stable at least for 40 hours when operated at a current density of 400 milliampere per square centimeter. To gain insights into the mechanism for CC coupling is the key to understand why C2 compounds, that is ethylene and ethanol, can be formed with such a high selectivity in electrocatalytic CO2 reduction reaction. In thermocatalytic hydrogenation of CO2, we know that the CC coupling occurs between CHX, CHY species for the formation of hydrocarbons such as ethylene, and between CHX and the non-dissociative CO species for the formation of C2 plus oxygenates such as ethanol. In electrocatalytic CO2 reduction reaction, the current consensus is that the CC coupling occurs between two adsorbed CO species. Our DFT calculations indicate that the coupling between the CHO species, the formula species, is energetically more favorable than that between two adsorbed CO species on copper surfaces, and the modification with the fluoride species significantly decrease the energy barrier for the formation of this formula species. So by combining the theoretical and experimental studies, we propose a hydrogen-assisted CC coupling mechanism. We found that fluoride not only enhanced the CO adsorption by enriching the surface copper plus sites, but also activated water activation to atomic hydrogen to assist the formation of CHO species, whose coupling is more favorable. This CHO species was observed by in situ electrochemical infrared spectroscopic measurements. Here I move to the last topic of photocatalytic coupling of methanol to ethylene glycol. Methanol is also an abundant and cheap C1 molecule that can be derived from different resources directly or via syngas. Methanol to hydrocarbons such as olefins and aromatics through MTO or MTA process, and acetic acid via carbonation are well-known processes involving CC bond formation. Here I focus on photoenergy driven methanol to ethylene glycol route. We call this route the MTEG process. Ethylene glycol is a key bulk chemical, in particular for the production of polyethylene terephthalate, the so-called PET plastic. The conventional routes for EG synthesis include the petroleum-based route via ethylene and ethylene oxide, and the coal-based route via syngas and methyl oxalate. Both processes have problems of high energy consumption, high emission, lower efficiency, complex multiple steps. The dehydrogenative coupling of methanol to EG and hydrogen is a very attractive reaction for EG synthesis. This reaction cannot be performed by thermal catalysis now. We expect that over a semiconductor photocatalyst, photogenerated electrons work for the hydrogen evolution, while photogenerated holes may function for the oxidative coupling of methanol to EG. However, other oxidation products such as formaldehyde, formic acid, CO, and CO2 may also be formed at the same time. Actually, over typical metal oxide semiconductors such as titanium oxide, formaldehyde was a major product. Ethylene glycol was observed over few metal sulfide semiconductors, and cadmium sulfide showed the unique performance for selective formation of ethylene glycol and visible light, and the selectivity of ethylene glycol was 71% over this semiconductor. But the efficiency of this semiconductor's cadmium sulfide alone was quite low, and the quantum yield of ethylene glycol was only 0.2% at the wavelength of 450 nanometer. To further increase the formation rate of ethylene glycol, we investigated the effect of co-catalysts. All these co-catalysts could accelerate the evolution of hydrogen, but most of them, for example, platinum, palladium, nickel oxide, accelerated the formation of formaldehyde more than that of ethylene glycol, leading to lower selectivity of ethylene glycol. It is unique that the two-dimensional molybdenum sulfide nanosheet not only accelerated the formation of hydrogen and ethylene glycol, but also increased the selectivity of ethylene glycol. So the modification of cadmium sulfide nanorow with three-dimensional molybdenum sulfide nanoform to facilitate the charge transfer and hydrogen evolution significantly enhanced EG formation. The selectivity of ethylene glycol increased from 71% to 90%, and the ethylene glycol formation rate increased for about 24 times, reaching 11 millimole per gram per hour. The catalyst was also quite stable for at least 100 hours, giving an EG yield of 16%. The EG quantum yield reached 5% at the wavelength of 450 nanometer. Our control experiments for methanol conversion in the presence of different scavengers confirm that hydrogen is formed by the photogenerate electrons, while EG is formed by photogenerate holes. Because the addition of radical scavenger almost stopped the formation of ethylene glycol. So the formation of ethylene glycol may proceed through a radical intermediate. So we performed in situ ESR studies to characterize the radical intermediates. Our results show that both hydroxymethyl radical and the methoxy radical were observed on our catalyst and light irradiation, and the intensity of this hydroxymethyl radical was much higher than that of the methoxy radical. It is reasonable to consider that the hydroxymethyl radical comes from the CH bond activation and is for EG formation, while the methoxy radical comes from the OH activation and is for the formation of formaldehyde. Therefore, these results suggest that the inert CH bond in methanol is preferentially activated on our catalyst and the visible light irradiation. It is known that the proton transfer and electron transfer are crucial steps in the activation of either CH or OH bonds to radical intermediates. There are two possible pathways. The first is stepwise proton transfer electron transfer pathway, and other is a concerted proton electron transfer pathway. So when the stepwise proton transfer followed by electron transfer pathway needs high energy barrel, the reaction tends to proceed through the concerted proton electron transfer pathway. So our DFT calculation result reveal that on the reference semiconductor titanium oxide, the OH bond in methanol is easily activated through the proton transfer to the methoxy anion and then to methoxy radical via the electron transfer, finally forming the formaldehyde. On the other hand, on the carbon sulfide semiconductor, the OH bond dissociation is quite difficult, needs higher energy barrel, and thus methanol undergoes concerted proton electron transfer to break the CH bond to the hydroxymethyl radical, and the easier desorption of this hydroxymethyl radical assists the formation of ethylene glycol. And this can explain the interesting chemistry of the preferential activation of the CH bond in methanol molecule. Although this titanium oxide cannot work for the activation of CH bond in methanol due to the presence of OH bond, it is able to catalyze the activation of methane molecule, which has only the inert CH bonds. Ethane and ethylene were formed as the major products via the coupling of the methyl radical, the intermediates. Very recently, we have also found that the exposed facet of titanium oxide nanocrystals affect the product selectivity and formation rate. The 0,10 facet shows higher selectivity and rate for the formation of the coupling products ethylene and ethane. So the selectivity of ethylene and ethane reached 50% over this titanium oxide 0,10 facet loaded with platinum nanoparticles. And the formation rate of C2 products reached about 0.3 millimole per gram per hour. Although the performance needs to be further increased. There is no doubt that the photocatalysis has provided a promising strategy to activate and transform methane to C2 compounds under mild conditions. I come to the conclusions. I believe that I have convinced you that tandem or relay catalysis is an effective strategy for the hydrogenation of CO and CO2 to C2 compounds with selectivity that can break the limitation. The design of matchable multifunctional systems working in tandem is the key. The combination of metal oxide such as zinc zirconium oxide, zinc aluminate for CO and CO2 to methanol, and zeolite such as SuPo34, ZSM5, and MOR for CC coupling offers a variety of valuable products such as lower olefins, aromatics, ethanol with high selectivity. The knowledge on the activation of CO, CO2, and hydrogen on metal oxide should be further deepened in the future. A significant progress has been achieved in the electrocatalytic CO2 reduction to ethylene and ethanol. Based on gas diffusion electrode and modified copper catalysts, the current density and C2 plus Faradic efficiency reached larger than 1 ampere per square centimeter and larger than 80% respectively. The single pass C2 plus yield exceeded 15% with selectivity of larger than 85%. But stability should be further improved, and the mechanism on CC coupling needs further elucidation. Photocatalysis offers a promising method for CH activation under mild conditions. Metal sulfide semiconductors catalyze the preferential CH activation of methanol, offering ethylene glycol with 19% selectivity. And efficient semiconductors that are capable of catalyzing methane conversion to C2 products are expected. Finally, I would like to thank all the staffs and the students in my group. In particular, Dr. Shunji Xie, Dr. Jing Can Kang, Dr. Kang Chen, Professor Qin Hongzhang, Mr. Wen Chaoma, Mr. Wei Zhou, Mr. Chen Zhou, Dr. Xiaoliang Liu, Dr. Xiaobo Peng, Dr. Ze Bingshen, and many of my collaborators, such as Professor Jun Chen of Xiamen University for DFT calculation, Professor Mingshu Chen of Xiamen University for XPS characterizations, Professor Dehui Deng of Dalian Institute of Chemical Physics for the synthesis of molybdenum sulfide nanoform, Professor Zhen Jiang, Professor Yang Pan, Professor Lu Mingpeng, Professor Chao Ma, and Dr. Jing Yu Ye for many characterizations. Also, thanks to financial support from the National Natural Science Foundation of China and the Ministry of Science and Technology of China. Thank you very much for your kind attention.